Okay, so let's go through these problems on permutations and combinations that we had on the worksheet on Monday. So here's the first question, and it's two parts. They're similar questions, but not exactly the same. The first question says, suppose we have a group of 18 workers. How many ways can a committee of 5 workers be selected from the 18? The second one, same 18 workers, but now it's 6 managers and 12 associates, and we want to form a committee of 5, but now we need 2 managers and 3 associates. So it's a specific kind of committee, so we should get a smaller answer for part B than we do for part A. So let's see how we do this. So for the first part, that's just our binomial coefficient, 18 choose 5. So this is a pretty straightforward combination. So ends up being 8,568 committees. For the second part, you have to break it down into the 2 tasks and use the multiplication principle. So for a lot of these ones that are not simple combinations or permutations, not straightforward combinations or permutations, you have to think of what's the sequence of things that I could do that would get me what I want, and then how many ways could I do that, use the multiplication principle, and make sure that at each stage you always have the same number of ways to do it. So in this case, choosing the committee is first choosing the managers, then choosing the associates, and the number of ways that you could do either of those is not influenced by what you do for the other. So they're completely separate tasks. So you can use the multiplication principle, 6 choose 2 times 12 choose 3. This is number of ways to choose the managers, number of ways to choose the associates. So 6, 5 over 2, 1, 12, 11, 10 over 3, 2, 1 makes 3,300 committees, which is certainly less than the 8,568. Second, how many distinguishable words can be formed from the letters of the word Florida? Okay, and here I told you in class I meant how many distinguishable words can be formed from all the letters. So use all 7 letters. This is a straightforward permutation problem. So this is exactly what a permutation measures. There's 7 possibilities for the first letter, 6 for the second, 5 for the third, and so on, all the way up to 1. So 7 factorial, 5,040 words. However, the next question is a little bit different, and this was what was confusing some people. How many distinguishable words can be formed from all the letters, so again, all the letters of the word Mississippi? So the thing to keep in mind here is that since there's repeat letters, the S here and the S here, or any of the 2 S's, you can't tell a difference. So if you switch 2 of them, it's the same. So what you want to do, maybe you want to think of like, one of the S's has a smiley face on. It's a happy S, one of them's a sad S, one of them's kind of in between, the other one's, has a hat on or something. Think that they're all different S's that you could tell apart, and then do the same thing for the I's and the P's, all the repeats. So pretend that you could tell them apart. Or maybe think of them as different colors, as a red S, a blue S, a purple S, a black S. If you could tell them apart, there'd be 11 factorial ways that you could rearrange them. But then you have to use the fact that you really can't tell the difference. So you would end up having to divide by the number of ways that you could rearrange the S's amongst themselves, the I's amongst themselves. That's a little bit more complicated way to look at it for now, since we're not going to go completely into this. So I'm going to show you a way that is definitely uses the multiplication principle and uses everything that we've used so far. And that's to look at it as the following. Okay, so we're trying to fill in the 11 spaces here. So there's 11 blank spaces. Now we can break the task of finding our word into figuring out where the M's go. So write down the M's, write down the I's, write down the S's, write down the P's. How many ways are there to do the M? Well, it's just 1 M, so there's going to be 11 ways. It's actually 11 choose 1. After you've chosen where the M goes, no matter where the M went, there's always 10 places left. So out of those remaining 10 places, you have to choose 4 of those for them to go. So 10 choose 4 ways to decide where the I's are going to be written down. And again, it doesn't matter where you put the M, because you always have 10 left over. Third task, where do the S's go? If you've written down all the I's and the M's, there's 5 places that have already gotten written on, so there has to be 6 places left. They might be different places, but there's still 6 of them. We have to choose 4 of those to decide where the S's are going to go. 6 choose 4 ways to do that. And in the P's, well, you're done, because there's 2 places left, and there's the 2 P's, and you have to write them down there. So choose 2, which of course is 1. And so I wrote this down. You could do each of these individually, multiply them together, but if you use the formula, an interesting thing happens. If you use the formula instead of the shortcut way that we were talking about, you get 11 factorial over 1 factorial, 10 factorial. But then the 10 factorial on the bottom ends up showing up on top on the next factor, over 4 factorial, 6 factorial, and then the 6 that are left ends up showing up on top, 6 factorial. So you get this kind of canceling thing that goes on. And so what you're left with on top is 11 factorial, and then you have 1 factorial, 4 factorial, 4 factorial, 2 factorial. And I'll leave it to you to think about, what kind of pattern do you think is showing up here in general? Could you generalize this to a more general kind of problem? What would be the pattern that you'd start to see? In this case, if you multiply all the numbers out, you get 34,650 words. If you're more interested in this kind of problem, you want to look up on Wikipedia or search online for something to read about. This is what's called a multinomial coefficient. It's a extremely important idea, extremely important object in math. It shows up many different places, especially when you're studying polynomials or counting things, number of ways you can do different things. So this is a really important idea, multinomial coefficient. Okay, number 4. How many distinguishable 4-letter words can be formed from the letters of the word logarithms if repetition is allowed? Now, logarithms has 10 letters, and they're all distinct. They're all different. So this is just a permutation of 4 out of 10. Now, words, the order matters. It's the first letter, second letter, and so on. So, for instance, the word, let's see. The word top, T-O-P, is different from the word pot, P-O-T. So it's not just selecting the 3 letters, it's the order that matters. So in this case, this one is repetition allowed. So in this case, excuse me, the first time I said this was a permutation. This first problem is repetition allowed. I misspoke. With repetition allowed, you're allowed 10 choices for the first letter, but then 10 choices for the second, because it could be still any of the ones. So it's kind of like you're drawing a card from a deck of cards, and then you're putting it back in. It's called choosing with repetition. So 10 times 10 times 10 times 10, we get 10 to the 4th, or 10,000 words. Number 5, so just let me go back real quick. Number 5, I said if repetition is not allowed. This is the permutation. Again, I misspoke on number 4. If repetition is not allowed, then you have a permutation because you have 10 choices for the first letter. Then you only have 9 remaining for the second, 8 for the third, 7, and so on. So 10, 9, 8, 7. 5,040 words. No, it's just a funny coincidence. That's also 7 factorial. Okay, last 2 questions. Get through this quickly. Experiment consists of tossing a coin 12 times, observing a sequence of heads and tails. How many different outcomes are possible? Okay, we're gonna, let's see. Okay. So we're gonna do this, when we do tree diagrams, we're gonna look at this more, but just for now, consider writing down 12 spaces, just like we were kind of doing for the words and the letters. But now you want to put a T or an H into each space. So every sequence of tails and heads you can represent by a sequence of T's and H's, what we'd call in math or computer science a string, character string. So T, H, T, T, H, would mean that you got tails, heads, tails, tails, heads to start. Well, there's how many ways could you get that sequence? Well, there's two possibilities for the first, tails or heads, times two possibilities for the second, times two. Because the number of ways that you can get tails or heads is the same no matter what happened on the previous tosses. So we get 2 to the 12th, 2 all raised to the 12th power, which is 4,096. Oops. Part B, how many different outcomes consist of exactly 4 heads? Okay, so this is actually a binomial coefficient. Because if you look at the 12 places, if you were to label them 1 through 12, 1, 2, 3, 4, 5, all the way up to 12, deciding where the 4 heads go is really like saying put the numbers 1 through 12 in a bag and then select out 4 of those numbers. So choose 4 numbers out of the numbers 1 through 12. So that's 12, choose 4. So maybe you want it in the 3rd, the 6th, the 7th, and the 10th. So that's one possible unordered selection. It can be a little bit confusing at first because you're thinking it's a sequence and the order in the sequence matters. But remember, when you're choosing the places, it doesn't matter what order you choose the places. So if you choose the 3rd, 6th, 7th, and 10th, that's not different than if you wrote down 6th, 7th, 10th, and 3rd. It doesn't matter what order you write the H's down, it just matters where you write them. So 12 choose 4, 495 outcomes. That's a binomial coefficient. Number 7, how many ways can a committee of 5 U.S. senators be chosen if no 2 senators can represent the same state? So 50 states, 2 senators each state, 100 senators. Again, you can't just do this in one step. You have to think of it as a sequence of things you're going to do and then use the multiplication principle. So probably the most straightforward way I think to look at this is to look at, first choose the states. Don't worry about who the senators are. You know that because there can only be 1 senator from each state, there's going to be exactly 5 states. So 50 choose 5 ways of doing the states. And then after you've chosen the states, say you chose California, well, you have to decide is it going to be Feinstein or Boxer. Okay, so you have choice 1 out of 2. So 2 possible ways to do that, but then you have that for every state. So 2 for the 2nd state, 2 for the 3rd state, and those are then 5 choices you have to make. So you get 50 choose 2 times, 50 choose 5 times 2 times 2 times 2 times 2 times 2, 2 to the 5th. If you multiply all those together, you get a very large number. It's 67,800,320. So that's the number of 5 senator committees in the Senate where all the senators are from different states. Okay, so I'm going to put up another video now to do with Pascal's triangle, and it's kind of just an extra little topic just to throw out there. It's not something you're really going to be responsible for, but it's an interesting thing. So I'll see you on Wednesday and Friday, and I'll see you later.